All right, let's get right into it. Today, we're talking about a technique that is so powerful and, surprisingly simple for solving a whole bunch of recursion problems. And it really all starts with one big question. What if I told you there's a master key for recursion? I mean, a single mental model that can unlock all these different tricky-looking recursive problems? Well, that's no exaggeration. That's exactly what we're going to build today, and it's called the pick/not-pick method. Okay, so to forge this key, we need a lock to test it on, right? And for that, we're going to use the subsequence sum problem. It's a real classic, and honestly, it's the perfect way to see this whole technique in action. So here's the deal. You're given an array, let's say 1, 2, 1. And your mission, should you choose to accept it, is to find all the different combinations of these numbers, we call them subsequences, that add up to a target sum. In this case, the target is 2. Now, you can probably see the answers already, right? It's got to be the two ones, 1, 1, and of course, just the number 2 by itself. So the big question is, how do you find those answers systematically without just guessing? Well, this is where the pick-not-pick method comes into play. This is the absolute core idea, the fundamental choice that's going to drive everything we do from here on out. And it's pretty much exactly what it sounds like. For every single element in that array, you face a fork in the road. You have two choices, and only two. You can either pick it and add it to your current subsequence, or you can not pick it and just move on. Every time you make a choice, you go down a new path. And by doing this over and over, you end up exploring literally every single possibility. Okay, let's actually walk through one of these paths just to make it super clear. So we're at the beginning, index 0. We see the number 1. Let's decide to pick it. Cool, our sum is now 1. Next up, the number 2. This time, let's say we don't pick it. We just skip it. Our sum is still 1. We move to the last element, which is another 1. And let's pick this one. Our sum goes from 1 to 2. And boom! Our current sum is 2, which is our target. We've just found a solution, 1, 1. All right, so we've got the basic concept down. Pick or not pick. But how do we turn that into actual code, into a solution? Well, this is where we get into our 3 patterns. Let's kick things off with pattern number 1. How to find and print every single solution. So for this first pattern, our goal is to leave no stone unturned. We want to be totally exhaustive. The idea is to make our code travel down every single possible path. And anytime it hits a path that works, where the sum matches our target, we just print it out. So what's the logic look like? Well, first, you need a base case, a stopping point. For us, that's when we've reached the end of the array. At that point, we check, does our current sum equal the target? If yes, great, we print the subsequence we've built. Now, the recursive part. For the pick path, we add the element and its value, then we make the next recursive call. For the not pick path, we just make the next call without adding it. But here's the absolute game changer, the most crucial step, backtracking. Think of it as an undo button. After a pick call is completely finished, you have to remove the element you just added. This makes sure your state is clean for all the other paths the recursion is going to explore. And that's exactly what this quote is getting at. It's that cleanup step. When you come back up from a recursive call, where you picked something, you have to undo that choice. You pop that element right back off your list. Why? Because it resets the slate. It makes it so the next branch of recursion starts fresh, without being affected by choices made down a totally different path. Okay, that's great if you need every answer. But what if you don't? What if your boss just says, hey, find me one solution, I don't care which one, and do it fast? Well, that brings us to pattern number 2. It's a much more efficient way to go about things. Yeah, the new goal here is all about speed. The moment we find a single valid subsequence, we want to slam on the brakes. Just stop all other recursive calls. There's absolutely no point in continuing to search if we've already found what we were looking for. So how do we pull this off? How do we stop early? The trick is to change our function so it returns a value, specifically a Boolean, true or false. True means, hey, a solution was found on this path, and false means, nope, nothing here. So in our base case, if the sum matches, we print our answer and immediately return true. Then, here's the clever bit. We wrap our recursive calls in an if statement. If any of those calls returns true, we don't even bother with the other calls. We just immediately stop and pass that true signal right back up the call stack, effectively shutting the whole operation down. And that's the core idea right there. It's like one of your recursive calls deep down in the call stack finds a solution. It then gets to shout back up to its parent, hey, I got one. And that parent then shouts to its parent, and so on. As soon as that message gets passed up, there's just no need to make any more calls. You found what you needed, job done. All right, let's tackle our third and final pattern. This one is for a different kind of question altogether. Imagine you don't need to see the solutions. You don't even need to find one of them. You just need to answer a simple question. How many solutions are there in total? Yep, our goal here is just to return a single integer, the total count of all the subsequences that add up to our target. We're not storing anything, we're not printing anything, we just want that final number. So the logic changes just a little bit, but you'll see it follows the same core principle. Now our function returns an integer. In the base case, if we find a valid solution, we return 1, as in we found one solution here. If it's a dead end, we return 0. And then, this is the really elegant part. The total count for any given step is just the count we get back from the pick path plus the count we get back from the not pick path. We just add them all up as they come back up the call stack. And just look at how this all comes together. This is what's so cool about this whole approach. The core recursive structure, the pick, not pick logic, it doesn't change at all. The only thing that changes is a tiny little tweak in the base case. What you return when you find a solution. You can print it, return true, or return 1. And that one small change completely transforms what the entire function accomplishes. That, right there, is the power of this pattern. So let's just take a step back and appreciate what we've built. This isn't about memorizing 3 different algorithms. Not at all. It's one single unified framework. It really is your recursive master key. This cheat sheet basically says it all, doesn't it? The goal dictates the logic. If you need to print all the solutions, you explore both paths and backtrack. If you need to find just one, you use that Boolean return to stop early. And if you need to count them all, you just sum up the 1s and 0s from your recursive calls. But that engine, the pick, not pick choice, that stays the same every single time. Now, there is one really important thing to keep in mind: performance. Because for every single element in our array, we make 2 choices, right? Pick or not pick. So if you have n elements, the total number of possibilities you explore is 2 times 2 times 2, n times, or 2 to the power of n. This is what we call exponential time complexity. And what that really means is this approach is super elegant, but it can get really slow if your input array is huge. It's a classic trade-off in programming. You're trading raw speed for a simple, understandable solution. So if there's one thing you walk away with today, let it be this. You didn't just learn 3 different ways to solve 3 different problems. No, you learned one core idea, one super flexible technique that you can now adapt to solve a whole class of problems just by making a few small tweaks. And believe me, this isn't just for subsequence problems. This pick-not-pick idea is the foundation for solving problems with combinations, permutations. It's even a stepping stone to understanding more advanced things like dynamic programming. So really, now that you have the key, what other problems are you going to unlock?